I'm going to talk very briefly about the exam and what you're doing. So, in some ways, the midterm is an extension of homework 3, using the same wave functions, the same system, except we're measuring something different than bond length in the midterm. So again, we have the idea is that actually we're dealing with two different molecules, HCl, and I'm going to write HCl kind of in the old-fashioned way because I think it's important. Right? It's got 3 lone pairs versus OH, which is a radical. All right, we're looking at these two molecules, and we're looking at their infrared spectrum. Right? We're exciting vibrations in a molecule, and I'm interested in the anharmonicity of these molecules, right? Remember, in the harmonic oscillator, the only thing you can do with light is excite the system by 1 quantum, right? You can go delta V plus or minus 1. That's all you can do. But if your system is appreciably anharmonic, you'll see other transitions, the 0 to 2, the 0 to 3. See what we call these overtones. These things become allowed. OH and HCl both show overtones, say, but they're much weaker than the fundamental. So the 0 to 1 transitions are very strong, and then the 0 to 2 are much weaker. They're not 0, they're still there, but they're much weaker than the 0 to 1s. And the only reason why they're weaker is because they're only allowed when the system is anharmonic. They're not allowed if it's perfectly harmonic. So what you ultimately are going to calculate is using our rules of harmonic oscillators and our integrals and different things to calculate the intensity ratio between the overtone and the fundamental. All right, that intensity ratio for the harmonic oscillator is 0. The overtone is forbidden, but these molecules are slightly allowed, and it's use these integrals to calculate the actual intensity ratio of these two peaks. So on Canvas, I just wanted to remind you, I posted a while ago. Let me just move my browser over to the other screen. Under announcements, I posted a couple of I would call it they're real spectra, but they're not real spectra. I didn't take them experimentally, but they're based on real experimental data. The spectra for HCl and OH. And so here's the fundamental transition. Right, this is your 1 to 0, and you'll see that roughly twice the frequency or twice the wave number, right, 30,000 to about 5,800, the 0 to 2 shows up. And you can see that the intensity ratio is very large. It's about a factor of 100. Right? The intensity of this peak goes down to 0, right? So it's basically normalized to 1. And this peak only goes 0.025. And they're about 100 times, 40 times weaker. Okay. And this intensity difference between the fundamental and the first overtone is dependent purely on the anharmonicity of the bond, or in this case, the dipole moment, as we'll see in this problem. And then if you look at OH, again, the spectrum doesn't look too much different because they're both diatomics. It's got a slightly different pattern, but don't worry about that. That's not important. What you can see is that the overtone in this is much stronger. Right? They're about 15 to 1 instead of 50 to 1. Okay? And so this problem explores that difference between OH and HCl. Okay? So you're actually going to calculate what you come out of this is the ratio of the intensity of this line to this line. Right? The intensities of each of these lines are dependent on an integral. And I'll talk about that integral in just a second. So basically, this problem ultimately reduces to 2 integrals per molecule, so a total of 4 integrals. You have to calculate the intensity of the 0 to 1 and the 0 to 2 for each molecule. That's an integral for each. Right, so this problem is very repetitive. You're doing the same thing over and over again, but what you're doing is you're maybe adjusting the final wave function in your integral, or you're adjusting the values to switch between HCl and OH, right, because they have different bonds. Okay, so it's really good to kind of organize your thoughts for this and realize that you're doing the same thing for 2 different molecules. You build your expressions up and you do everything so that you can just plug in the values for each molecule, then it's a really easy thing to do, right? You just set up the equations once and then plug in the values for each molecule and you're good to go. You calculate a ratio. All right, so this is kind of the crux of the midterm, the middle part. So I just want to talk very briefly about, just remind you of the theoretical principle of this. The idea is that a vibrational transition, right, absorption only appears when the dipole of the molecule changes upon vibration, right? When you stretch the molecule along the coordinate, the normal mode, the dipole changes. If the dipole doesn't change, then you don't see a spectrum. Okay, it's forbidden. So what we're doing is we're taking these two molecules, which are initially at some length r sub e, right? And what we want to do is we want to think about how does, and they have some dipole moment, of course. Let me just say that really quickly. Right? They also have some dipole moment, mu. Okay. Right? And so as you stretch the bond, to make the bond longer or shorter than Re, the dipole moment will also change, because the dipole moment is a function of the bond length. You think about it, right? You have you can think of this as a positive charge and this is a negative charge. As you extend the difference between as you extend the space between the positive and the negative charge, the distance between those charges increases, which makes the dipole longer. The dipole is increasing, at least we think it is, as you stretch the molecule. Okay, that's what we expect. So the idea is that we expect, right, I'm going to let x equal r equals minus re. So x equals, so we can compare both on the same plot, because Re is different for both molecules. They're both different by about 30%. What would we expect? Well, on a plot of x versus dipole moment, we would expect the function to look something like this. Right? A nice straight line. Actually, let me erase that. It's not going through 0. A nice straight line through some positive value where the vertical intersection, the intercept of this line, is the dipole moment at x equals 0, which is the equilibrium dipole moment, U sub e. Okay, right? That's the dipole moment we measure when we look at the molecule and we have it shining light at it. We ask, what's your dipole? We get the dipole right where the bond usually sits, right? And so we expect that the function will increase linearly as we stretch it, right? That's the expectation. And a harmonic molecule, a perfectly harmonic molecule, its dipole function will be a straight line. Right? So perfectly harmonic, we would expect that mu of x is something like mu of e, the intercept, plus some number c, whatever that number is, times x, where c is the slope. Right? And this gives us the harmonic approximation, and this gives us the selection rules that the quantum number can only change by 1, plus or minus 1. There would be no overtones. Right? So for something that's anharmonic, something that has an anharmonic electronic structure, an anharmonic dipole, then mu of x will not be linear, but it might have some other components that are nonlinear as well. So what would that function look like? Well, it could look like any number of things, right? It could look something like this. Right? Maybe it starts decreasing like that. It could look like that. It could also increase exponentially or like a power law like that, right? We don't know. But it could do any of those things. Depends on the molecule. Right? And so what happens if this happens, right? What if the dipole function is not linear anymore? Well, then our harmonic approximation breaks down. And the other transitions that are once forbidden, the 0 to 2, the overtones, become allowed again. And why did they become allowed? Well, this is the point of the problem, is to measure the intensity of the line, we have to measure the dipole moment and how it affects the connection between the initial state and the final state. So I kind of talk about this in the introduction, which I highly recommend you read carefully. Right? The intensity of some line, let's say, for instance, from 0 to some level j, is equal to the absolute value squared of the average value of the dipole, the function itself. Right? And how would we write this integral? Well, it's an integral from negative infinity to infinity of our final state wave function, psi j, times the dipole function itself, times the initial state we started in, which is psi 0, v equals 0, times dx. Right? You've done, well, and then we got to square the whole thing. Right? You take this value, this result, and you square it. Right? It needs to be a positive value. Right? So what is this integral telling us? Again, it looks just like the integrals you were doing in homework 3, except now the state on the left-hand side, the final state, is different than the initial state. Right? Because we're thinking about how the dipole affects us, allows us to move from one state to another. So you can think of the right-hand side as the initial state, and here's our final state. Right? When we measure a bond length, we're asking, in our initial state, when we measure the bond length, what's the probability we still end up in the final state that hasn't moved, right? That's psi 0 and psi 0 here. Right? So that's asking, what's the bond length, the average bond length, assuming the state isn't changing? That's the bond length. So an intensity is, what's the probability of changing states from 0 to j, whether that's 1, 2, 3, 4, whatever, upon measuring the dipole moment. Now, how do we measure a dipole moment? Well, the way we interact with a dipole is by shining an electric field or light at it. Right? So this measurement, right? Remember that the operator always represents a measurement. Right? This is the thing we measure. With light. Right? We shine light at an energy with a frequency that's equivalent to the energy difference between these two states. It's oscillating in time. And what is the property, the object or the operator that represents the thing that interacts with the light? Well, that's the dipole moment. All right? So what is this integral asking me? It's asking me effectively, what is the probability that when I start inside v equals 0, that when I interact with the system by using light, therefore measuring the dipole moment, what's the probability I end up in a new state j? That's all intensity is for a spectroscopic transition. It's saying that when I shine light at my system in initial state, what's the probability I end up in my final state? And what do we need to do to calculate that? Well, we'll calculate the average, which is the integral. Right? So this integral tells me exactly the probability of using light to move from one state to another. So if this value is not equal to 0, that means that there's some probability that when I shine light at this molecule, it goes from state 0 to state j. Okay, so what is this? Again, so the only integrals you have to calculate in this is to calculate the intensity of the 0 to 1 transition, right? That's the harmonic transition for HCl and OH. And then to calculate the probability or the intensity of the 0 to 2. And then you take the ratio. Right? Each of these intensities will be a number. Right? If the dipole is linear in the region where the bond is stretching, then the intensity from 0 to 2 will be 0, right? Because it's harmonic. The dipole moves linearly. You know, it looks like this green line. Then I 0 to 2 will be 0. This is forbidden by the harmonic approximation. And of course, 0 to 1 will be non-zero because that's allowed. Okay, but because we're going to assume, if you look at the table of the dipole moments, right, they're quadratic functions. So the dipoles for these molecules are in some ways inherently nonlinear. They have some quadratic behavior. And the question I'm asking you in problem 1 in particular is, in the vicinity of where the bond is stretching when you excite it, the range of values for that you can get from homework 3. Think about how much the bond changes in HCl in homework 3. That should tell you how much X is changing. you should find that one of the molecules looks very, very linear, and the other one looks very quadratic. Okay, so one molecule has a very harmonic dipole, which means that 0 to 2 will be very weak, if at all possible. And then you're going to have a molecule where the 0 to 2 transition is very strong because the dipole doesn't look linear in the region. Okay, so that's why I have you plot them, because you can immediately see that one acts very normal and the other one acts very funky. Okay, and then you're going to take that funkiness and calculate why it's funky. And then the last question on the exam asks you to use chemistry to explain the difference between the results for HCl and OH. All you need to use is Vesper theory, the octet rule, just very, very simple chemistry to at least give me an idea or a hypothesis why these two molecules show such different behavior. Right? You don't have to give me the exact reason. There is an exact reason why one molecule has a very funky intensity and the other one doesn't. But there's a good reason why I drew the two molecules the way I did here.
What did it say next to 3 under goals?
I'll calculate the ratio. Ratio of the intensities. Again, think about the electronic structure of these molecules, the bonds. One's a radical and one's not. That should give you a hint to think about why one's funky and the other one isn't. All right? So just think about those things. Use a little bit of organic chemistry, a little general chemistry to come up with a hypothesis. If you want to figure out the real reason, that's great too. And in fact, I will tell you the answer to the real reason later in the class before class ends. We'll actually talk about it. You can probably guess which one's the funky one, but I'll let you decide that on your own. Any questions about this? Okay. Good luck. And again, I'm more than happy to meet with you at office hours on Friday if you have any remaining questions. And you can also email me. All right, let's continue. So I want to talk, we're going to spend the rest of the week talking about angular minimum. We're going to get back to the hydrogen atom next week. We'll finish it up next week, and we'll be done with the hydrogen atom. Right? Well, we only need, once we talk about angular minimum for a couple more days, we'll have enough information that we can tackle the radial part of the hydrogen atom, right? The potential as a function of distance between the proton and the electron. We can do that in one day. Right? It's really straightforward. The math isn't straightforward, but I'm not going to go through the math. I'll just skip all the hard math and come to the results. So we'll get through that next week. We'll talk about the hydrogen atom, and then we'll start thinking about atoms with more than one electron, and then we'll start thinking about putting atoms together to make bonds. So we're getting close to molecules, very close. So I really want to focus a little bit about the angular minimum of this electron around a proton, because the theory of this, the quantum mechanics of angular minimum, very, very powerful and ubiquitous in science. It's not just rotating molecules like what I study or electrons rotating around protons. There are deep consequences for the laws and the physics of angular minimum in quantum mechanics. And we're going to learn some results today about the spinning of this electron that we can directly use to describe the spin of the electron. Right? Going all the way back to homework 1, thinking about color and flavor. We'll be able to talk about why those are incompatible measurements this week. Right? We'll have an answer for that by Thursday. So in some ways, we'll get a good chunk of this information about theory about spin about an electron through this stuff. Okay, so let's just recap where we were. We had again, we're always working on this XYZ plot because we're in 3 dimensions. We always choose Z to be in this direction until I otherwise notate otherwise. We're going to put that proton right smack in the middle of our axis system, and we're going to connect it through a tether of fixed length r, which is a vector which points at the electron at the tip of the vector. Okay, so this is our coordinate system. This is the coordinate system of the hydrogen atom if you were standing on the proton looking at the electron. Right? We're going to have to think about our frame of reference when we talk about these physics. But these physics are basically implying that the proton's not moving. So what we're literally doing is standing on the proton and pointing to the electron and watching it track around us as we don't move. Okay, so this is the atom fixed axis system. We call this atom fixed axis, or reference, or frame of reference. All right, which is useful for us. But we might want to start thinking about what it looks like in the lab as well, right? We're also going to have a laboratory system frame of reference where our z-axis is up and down in a room and left and right. Because the proton, right, the system may be spinning from our perspective, but we don't notice that spinning when we're sitting on the proton because we only see the relative motion of the electron, right? In the same way that the Earth is orbiting, but in spinning, we don't notice that because we're standing on it. The system can also do that as well, and we don't notice it because from our frame of reference, it's stationary. Right? That's the equivalence principle. Right? Equivalence principle is there's always a frame of reference you can choose that makes it look like the object you're looking at isn't moving. So we're choosing the frame of reference where the proton is not moving. All right, and we're going to orbit. We're going to make this thing spin, this electron spin. So we're going to apply some momentum to the object. Right, so maybe we push the electron in this direction, right? And remember, it's tethered to the proton, so it can't fly off. So this thing's going to orbit, and the question is which way is it going to rotate or orbit around the proton? Well, we can determine that by calculating the angular momentum, L, angular momentum, which is the cross product of R times P, cross product of R and P. And remember, just as a reminder, we use the remember, so a cross product, a vector that's a cross product of two vectors is perpendicular to the plane of the two vectors that you cross. So I'll just kind of roughly draw that plane. Right, it's the x in this drawing, it's the xz plane. I'll just kind of draw it, right? You have this plane here, and the angular momentum vector is going to stick straight out of the void. Right, so the angular momentum is in this direction. So I'll kind of draw a big fat arrow sticking out. And it's roughly in this direction. This is L. Right, and of course L, if the R and P are my hands, if the plane drawn by R and P are my hand, angular momentum is sticking straight out. Okay. All right, another way to look at this is that if we align our system along the angular momentum axis, right? What if I instead draw it like this? Let me get this right. Let me draw it like this, actually. Just a sec, guys. This is going to be a tricky picture, but I'll do my best. Oops, sorry. Get it from here. So I'm trying to draw a three-dimensional circle, or a donut, so I'm just going to do it by hand. So we've got a donut here. Kind of sketch it a little bit, so this is the back side of the donut. And then we have a axis system going through the donut, like this. This is going to be our angular momentum vector, right? And this donut is our electron orbiting, or something spinning, right? So this donut of angular momentum, or of inertia, this is our rotating system, right? When you have an angular momentum pointed in this direction, right, you can imagine that the proton is right here in the middle of this donut, and the electron is sitting here. Right, the electron orbits counterclockwise with respect to the axis at some angle, at some frequency omega. Okay, so the angle of rotation, right, if I stick my thumb out in this direction, the angle of rotation is how my fingers curve in my right hand. Right, so if it was rotating the opposite way, it would rotate clockwise from this perspective. All right, and again, the idea here is that the length of L, classically, is the moment of inertia times the frequency of the rotation, which for the hydrogen atom this is, the mass of the electron times the distance between the electron and the proton squared times the angular frequency, omega. Okay, so we got this electron rotating like this if we spin it up. Okay. So again, this is all classical, but the vector approach is very useful for us because we can represent these things as vectors, and if we can think about how we add and subtract vectors and think about how vectors are pointing, it tells us something about the angular behavior of our system. It's not perfect because it's classical, but at the very least it gives us a nice physical interpretation and intuition about what's happening to this electron as we spin it. Okay, so we want to take this system and we want to, again, convert it to quantum mechanics, which we kind of did last class. And I'll just remind you of the results. We spent a good amount of time on it. Right? We showed that L squared over 2I, so the square of the angular momentum divided by 2I, is equal to the kinetic energy. Okay, so that means then that if we're allowing this system to have free rotation, right, so no potential energy, if we're allowing the electron to rotate freely, no potential energy, then the Hamiltonian of this system is 1 over 2I times the angular momentum operator squared. Okay, right? Because there's no potential, the system can rotate freely. That means the Hamiltonian is all kinetic energy, it's only kinetic energy, and therefore it's proportional to L squared. Okay, so if we can figure out the wave functions that satisfy, right, we can take this expression, and what do we want, right? In quantum mechanics, we want to find the eigenvalues and the eigenstates, the wave functions in the energies, or the angular momentum, right? We want to find wave functions such that when we apply L squared to them, we get a number back times L squared, times psi. Right? That's always what we want, and we want wave functions that represent the rotations of our system. Right? And we also want to find the allowed values of the number. Right? Remember, and when we talk about energy, we want to talk about the allowed energies of our system, right? And so this is also the allowed values of angular momentum. If we divide those values by 2I, then we get the energy. Right? And this also says that these numbers divided by 2I are the allowed energies. Okay? So I didn't go through this math with you, right? We didn't actually derive them. I just gave you the results. And the results are very nice, right? We find that when we apply L squared to our wave functions, we get h bar squared times this new number j plus 1 times psi. Right? And these are our allowed values for L squared. Okay? And j can be any positive integer or 0. Okay? Right? Just like vibrations, right? V, we get a factor of V. V can be 0, or V plus 1/2. V can be 0, 1, 2, 3, 4, right? Those are our allowed values of vibration. And here we have the same thing. We have allowed values of angular momentum. Right? What this means is that we can only spin the system up in discrete values. There are certain angles, there's certain speeds that our electron can't have. Right? We can only have very specific values of L, or L squared. Okay, and again, I'll just remind you, we'll just look at them one more time. And our wave functions here, our solutions for this, actually take two numbers j and m, and they're functions of theta and phi. And these are what we call the spherical harmonics. These functions y that have two labels, j and m. I have them wrong, or do I? Just a sec. Yeah, sorry. So I have it here. Do I have the m on the top
Yeah.
and j at the bottom? Yeah, there we go. Theta, phi. These are called the spherical harmonics. All right, when we talked about this, I'm not going to reiterate things again. You know, remember j equals 0, right? The 0, 0 spherical harmonics is sphere, right? What that means is that the electron can be anywhere in a sphere around the system. And then we had the things that look like p orbitals and d orbitals and so on and so forth. Right? That's where these orbitals come from, are from these spherical harmonics, right? From the rotational behavior. All right, so I want to go back and talk a little bit about this m number today. All right, we really haven't talked about it too much. We understand j. So j measures the total angular minimum of the electron, right? How fast it's spinning. Right? L is proportional to omega, right? R squared and me, they're fixed. Right? So L squared is going to be proportional to the angular frequency. The faster it spins, the larger L is. So I just want to show you some spherical harmonics. I found this picture on Wikipedia. It's really, really cool. And I thought I'd show it to you. So I go to modules. I posted this down in module 3. First result, table of spherical harmonics on Wikipedia. And these actually give you the functions for all the spherical harmonics. Don't have to worry about that. You're not memorizing them. I'll give them to you when you need them. But I wanted to show you a really interesting picture. Is this one animated? It's not. Oh, it is. So let me zoom this in a little bit. Oh, this should be animated, but why is it not animated? Ah, there we go. Perfect. All right, so these are polar plots of the spherical harmonics. So they're rated by J, which they call L here. Right? Remember, there's two J plus 1 M states. So J equals 1 has 3, J equals 2, the D's have 5, the F's have 7, so on and so forth. And you can actually see the angular momentum here of the phase. Right? So the J equals 0, M equals 0 state, right, the rotational ground state of our electron, is just a sphere where the value, or rather the probability of finding the electron, is the same everywhere. Right? This is what we call an S wave, right? An S orbital, right? It's just a sphere, this electron cloud, as we call it, right? See, that electron cloud isn't a very good term to use because that implies there are many electrons here, but rather it's just that the probability of finding the electron is uniform across the entire surface of the atom. It can be anywhere. And so, again, these don't quite have the same lobe shape that we want, but it at least shows you the angular momentum property of the system. Let me show you the other. Actually, I don't like this one as much as the other one. So there's actually two different plots here, and I think the ones that are plotted on circles are a little easier to see. I regret picking that one. Okay. So here what we've done is we've actually projected we've taken psi squared, if you will, the wave function of the spherical harmonics, and projected it as colors, which the colors tell you something about the phases of the wave, right? So there's like a positive trough and a negative trough and a positive trough and a negative trough. Right? And so again, there's no troughs in the J equals 0 state because it's a sphere. It's uniform. Right? You can see the difference now between the J equals 1 states, right? Well, now we've started to add some angular momentum to our electron. It's now formally rotating. Formally has some angular momentum. And so here you can see them spinning. The electron, effectively, this is the phase of the wave function of the electron is a function of time. That's what the colors are. Right? It's the peaks and troughs of the electron wave. And you can see depending on which m I choose, minus 1, 0, or plus 1, it changes the axis of rotation. Right, so let's look at the m equals 0, 1. Right, you can see that as this the sphere rotates, which you can't really see, the phase isn't changing in this cutout. Right? It's red in the northern hemisphere and white in the southern hemisphere. Right? So this electron is if you think about the proton being in the middle and this is the z-axis, the electron effectively is orbiting in the xy plane around the equator of the proton. Right? It's rotating equatorial. But if you look at these two right here, now they're a little hard to tell apart, but you can tell by the phases, the color changes, that they're slightly different. What we're doing now is we're rotating, instead of along the equator, we're rotating along an axis through the sphere that is slightly tilted away from the equator. It's actually at 45 degrees, roughly. Right? So instead of it rotating like this in the xy plane, it's rotating like this, right? It's precessing about the z-axis instead. Right? And you can see that now it has a slightly different angular rotation, right? So again, if you were to represent the rotation of the Earth, right, you would say that it largely has m equals 0 character. Right? Because it rotates roughly on its equator. It's tilted by what, about 4 degrees off the equator, its rotation, but it's basically something like m equals 0. So this is the important thing. Remember, the Earth, this implies that the only possible degrees of rotation for one unit of angular momentum is either right along the equator or plus or minus 45 degrees. There's only 3 orientations for the rotation of this electron at j equals 1. Whereas for the Earth can choose any axis of rotation at once, right? It has one at 4 degrees. There are planets that rotate, so I think Neptune's, for instance, I think it's Neptune and Uranus, its axis of rotation is 175 degrees. It's upside down. It rotates the opposite direction as the Earth. Some planets are more tilted than others. I'm not sure what all the tilts are. Right, so there are plenty of stable rotation solutions for a classical sphere. They can point in any direction they please. But a quantum mechanical rotor, especially when it only has exactly 1 unit of angular momentum, there's only 3 orientations it can choose from. And there are 5 for j equals 2, 7 for j equals 3, and so on. Okay, this is where that discrete nature comes in. There's certain orientations. So this should give you a hint about what m is. Right? J determines how fast the system is spinning, and m tells you something about the angle, the direction at which the system is rotating with respect to. All right, so let's look at that a little more carefully. And what we'll find is that, again, that m number has everything to do with this axis of rotation. Any questions so far? Okay. So let's move to another frame of reference just one more time for our vectors, and this one's going to be very, very useful for us.
Can you go back to the last slide?
Of course, of course. Yeah, go ahead. What can I do for you?
Yeah, it was, all that.
Okay, so look, while we catch up on writing, let me chat just a minute about what I'm about to talk about. We've identified quantitatively that the J number has something to do with the magnitude of the angular momentum. All right, it's how fast you spin. And we saw that in those plots that m has something to do with the way that the angular or momentum vector is tilted with respect to the axis, right, the poles of the atom, if you will, or the sphere, the north-south poles. So m has something to do with direction. Okay? And that should be useful because what we're doing when we measure L squared is we're measuring the speed, the magnitude of the rotation. But we don't know if it's rotating clockwise. We don't know if it's rotating counterclockwise. We don't know if it's precessing around the equator or around the northern pole, right? We don't know anything about the orientation of the rotation. Right? And of course, for a vector, we need to know direction and magnitude. Right? It's not just a scalar quantity. Right? This is our scalar, L squared. Tells you about the magnitude, right? The speed, if you will. But remember, velocity or momentum is a vector. It has a directional component as well. And m is going to tell us something about the direction. Is it okay if I keep moving? We'll come back to this these topics. I'm still talking about these, so we'll see these equations again. Okay, so what I want to do is I want to shift my frame of reference just one more time. All right, we're going to move to a laboratory. Actually, no, I'm not going to say that yet. I'm not going to say that yet. I apologize. So let me just draw a coordinate system. And let's, instead of thinking about the axis, the center of this system, or the origin of this being at the proton, but rather at the object that's moving. All right, so let's set the electron now to be the origin. So now we're sitting on the electron, which of course is impossible because it doesn't have a size, it's a point. But imagine you're fixed at the location of the electron, and it has some angular momentum. All right, there's some angular momentum in some direction. Okay, so let's talk about this angular momentum, right? We know something about the magnitude. What's the magnitude? Well, the magnitude of the angular momentum is going to be the square root of the result of L squared, if you will, the average value of L squared, which is h bar times the square root of j plus 1. Right, so the length of this vector is h bar times the square root of j plus 1. Right, so that means the allowed angular momenta are, well, 0 h bar, right? That's where j is equal to 0. J equals 0. Then we have j equals 1. That's 1 times 2, square root of 2 h bar. J equals 2, that would be 2 times 3, that's 6. Square root of 6 h bar. And so on and so forth. Okay. You may notice that angular momentum is dependent. What are the units of angular momentum? Well, they're the units of h bar. Well, Planck's constant is actually, the units of Planck's constant are the SI units for angular momentum. That's where h comes from, right? This is actually explicitly, the Planck's constant explicitly has to do with something angular. Right? Remember, it converts between energy and frequency. Frequency means something's oscillating, which means it has angular momentum. Therefore, angular momentum is proportional to h bar. That's what Planck's constant is. It measures an angular property. Okay, so these are the allowed momenta, but the question is what's the direction? Right? Because there are plenty of vectors that have this length that have any direction, right? I can choose any vector along this circle. Let me make this actually a circle. I'm trying to undo this. Oh boy, it's making me do this. All right, so I'm just going to wing this. Well, if you imagine if I sweep a sphere, not even just a circle, but a sphere around the electron in all 3 dimensions, there's an equivalent vector with the same magnitude, right? I could draw a vector in this direction that has the same length L. Draw a vector in this direction.
Is that supposed to be square root of h for j equals 2?
Square root of 6.
Oh, okay.
Thank you. Right? There are an infinite number of vectors in 3-dimensional space that have this length. Right? So if I just define the length of the vector, I know nothing about how it spins. Right? So I got to come up with a direction. Okay, so we have to measure a direction. So how do we measure that? Well, we measure the x, y, z components of L. We say, what's the direction along the z-axis? Right? Just like we do with any vector, we measure it along the coordinate system, the components along the coordinate system that we define. Right, so there is, if I draw a little bit of a green line here, there's a vector here called L sub z, which is the angular momentum in the z component. And of course, there's another one along the x component. called L sub x. Right? Because L is a vector, and we can always write it as L sub x times x hat plus L sub y times y hat plus L sub z times z hat. Right? It's a vector in XYZ space. Now, I'm kind of moving between spherical and Cartesian coordinates, which I'm allowed to do. Of course, the math I'm going to convert back into spherical coordinates, but for our understanding conceptually, it's easier to think about things in Cartesian coordinates. Right? So what I want to do, and if I want to measure exactly how the system is rotating, I need to measure these three components. Right? I need to know Lx, Ly, and Lz. Unfortunately, quantum mechanics will tell us that we can only know one of them. We can make a choice. We can know one of the directions and not the other ones. So the only allowed choices are of things that I can measure are L squared with Lx, or L squared with Ly, or L squared with Lz. Right? I can only choose a pair of measurements. I can't choose all of them with L squared. I can only choose one. And I'm going to show you before the end of class today why that is. All right? And by convention, I can choose any one I want. It doesn't matter, because the only difference between x, y, and z is convention. So I always, in all of chemistry and physics, we always choose the z one. This is our choice by convention. Okay? And what that means is that there are only two things that I can measure about angular momentum. I can measure the magnitude, and I can measure its direction along one of the axes. Right? I can tell you, all I can tell you is if it's pointing this way, or somewhere this way. If it's pointing this way, it rotates counterclockwise with respect to us. And if it points this way, it rotates clockwise with respect to us. All right, or it could be along the axis as well, as we'll see. Okay, so we can only really determine the orientation of the net rotation. We can't really tell you if it's pointing x, y, or any direction. We can give you a sense of whether it's clockwise or counterclockwise, and how much is it precessing, or how far away it is from the equator. That's it. Can't tell you if it's pointing to the west or to the east or whatever. I can't determine that. And so when you do this math, and you go back and you think about the quantum mechanics of the z direction of L, what does that vector look like? What do the wave functions look like? Well, again, we found that L squared times psi gives us h bar squared j plus 1 psi, right? That's our magnitude. And then when we apply Lz to psi, we get a factor of h bar, because again, Lz has units of angular momentum, not angular momentum squared, so it's h bar, not h bar squared, times m psi, where m can be between j, minus j, and plus j. Right? This is where your p orbitals, why you have 3 p orbitals and why you have 4 or 5 d orbitals shows up. Is that when your j equals, say j equals 1, that's the p's, a little bit angular momentum, and there are minus 1. The only allowed values of m, are between minus 1 and plus 1. That's minus 1, 0, and plus 1. So just as an example, I'll just write that down, yeah, right? So for our j equals 0, m is equal to 0. That's an S wave. It's a sphere. J equals 1 gives me m equals 0 or plus or minus 1. This is P. J equals 2 gives me m equals 0 plus or minus 1 or plus or minus 2. This is D. And so on and so forth. So there are 2j plus 1 m values. Okay, so that's why we have two quantum numbers for our spherical harmonics. We first measure how fast it's moving, and then we measure the direction of the angular momentum relative to the z-axis. Is it spinning along the equator, or is it tilted to the north, or is it tilted to the south, which means clockwise rotation. Okay. So when I put this all together, and I'll just kind of draw it up here. I'm going to zoom out a bit so you guys can keep writing. If I put this on an axis system, and I let j equals 2, okay, what are the possible values of z, Lz? Well, Lz can be 0. It can be +1. It can be +2. It can be -1. And it can be -2. Okay? Right? So those are the ways that the vector can point, right? And the length of the vector, right? The length of the vector is square root of 6h bar. Right? So my m equals 0. This is m equals 0. It has length square root of 6h bar, and it's pointing along the x-axis, right? It has no component along the z-axis. M equals 0, j equals 2 means the electron is orbiting around the equator of the atom. But there are other possibilities, right? It can be +1. And it can also be +2. Sorry, I'll make that a little longer. And likewise, it can have equal and opposite clockwise rotation in the opposite direction. I'm just trying to make these as accurate as possible. Right, so the angular momentum can point in 5 different directions. It can point this is counterclockwise rotation, and this is clockwise rotation, or precession around the axis system, around the north and south pole, rather. Okay, so these are what your d orbitals represent. Electrons and j equals 2, d electrons, they can rotate in 5 different ways around the z-axis. 5 different precession trajectories. 5 different types of orbits. They all have the same angular momentum. They're pointing in different directions. Okay. The important thing is that, again, we only know z. So in fact, these vectors really aren't, it's not really one vector, but it's a collection of vectors along the xy plane. So if I were to draw the y-axis out a little bit further, like this, the vector here at +2 actually is a collection of vectors that orbits the z-axis, right? It can be along any, right? The angular momentum can be along any possible direction along the xy plane, just as long as the z component is fixed. So it's possible that the vector is like this, or like this, or like this. It doesn't matter. It's a combination of all of them, right? We can't determine that. So in fact, it kind of sweeps out a cone, if you will. The possible trajectories of an electron in a given angular momentum state sweep out a cone in the other 2 dimensions. It's completely uncertain. We have no idea how it's rotating with respect to x and y. No idea. Right? It's a superposition of all of them, completely undefined. And what we say is that if you think about it, there's a phase factor associated with rotating this, right? A phase associated with the position of the vector on this ring at z equals 2, and it's the energy in the angular momentum has no dependence on that phase angle around the system. Doesn't matter. It could be in any direction. Okay. So again, that's kind of a confusing thing, but the math actually, as I'll see in just a second, as we finish up in the last 15 minutes, I introduced to you a new postulate of quantum mechanics I haven't talked about yet, and we'll kind of work on it a little bit more on Thursday. I want to introduce it to you today. That will guarantee and prove to us, I don't know if prove is the right word, but it will give us a test, if you will, that will completely confirm that this is true, that we can only determine one direction at a time. All right, so we need some way to test this, if you will. All right, we need some way to make sure that this actually works out in quantum mechanics. Okay, so let me introduce this new postulate to you. I don't know what number we're on, so I'm just going to call it the next one. All right, and I'm going to introduce a new tool to you that's very important in quantum mechanics. It's called the commutator. Okay, so let me define what a commutator is first, and then I'll tell you what the postulate for the commutator is. Very simple. Well, I don't know if it's simple is the right word, but it's not too hard to calculate. The result's pretty straightforward. So let's assume, consider two operators, two different measurements. Maybe you can think color and flavor, A and B, okay? Such that when we apply A to some wave function, the wave function that we choose, we get a number back times the wave function. Okay? So the wave function satisfies the eigenvalue problem for A. And then 2, let's assume that when we apply B to some other wave function set, we'll say psi prime, we get B times some number B times the wave function psi, right? These are just numbers.
And those are prime, right?
Yeah, prime. Yeah, I'm not going to say psi and psi prime are the same yet. Okay, we're going to the postulate will tell us how to determine that. All right, so the question I want to ask is, the question I want to answer is it possible to find a set of wave functions that I can apply A to and B to and get answers back? All right, can I define a wave function such that psi and psi prime are the same? Okay, what does that mean? Well, that means, for instance, that if I have a set of wave functions that satisfies energy, H psi is equal to E psi, what are the operators that I can apply to those sets of wave functions that also give me numbers back? So for instance, position, right? We solve the Schrodinger equation for the particle in the box, and then we apply the position operator and we get everything works, right? So we know we can get the same set of wave functions for position and energy, right? But are there sets of operators that don't do this, where I can't determine both at the same time, that psi and psi prime are different? Right, so I want to determine that, whether I can determine both simultaneously. Okay. Psi is equal to psi prime if and only if I apply this product of operators. We'll talk about this product in a second. And I apply this to psi, I get 0. Or another way to write this, that the operators commute. That doesn't matter which way I take the operators. If I measure B first, then A, it gives me the same result as if I measure A, then B. Okay, so that's what that means here. Okay, so let's do an example. So let's assume that here. Let me define one more thing before we do an example. this difference of operators, AB minus BA, this is called the commutator. And we write it like this, with brackets. We put the operators inside the brackets, separated by comma, AB. All right, so this is equal to A, B, minus B, A. Okay, so let's talk a bit operationally about what we're doing here. So imagine, again, remember, operators correspond to things that we can measure in lab. So what am I doing here? So let me put it over here first. So we're going to do the left-hand side first. Psi is our atom. We put it in our box, and we measure B. Okay? We have some representation for our electron. We measure it with B, measure the quantity B, and then right afterwards, immediately after, we measure A. All right, we get some answer. Right? We get B. B is going to return the wave function. It may change it. It may keep it the same. I don't know. We measure A, get the result. And then what we're going to do the experiment again, but we're going to switch the order of operations. We're going to take the same system and measure A, and then measure B afterwards. Okay, if we get the same result on both sides, then this wave function satisfies both of these properties. Okay, we can measure A and B, right? Psi gives us information about both operators. But if I get a different result, if AB psi gives me a different answer than BA psi, then I can't measure both things simultaneously. All right, so we say that if two operators commute, which means that you can flip the order with no change, there exists a wave function or a set of wave functions we'll call them phi, such that when I measure phi with A, I get a number out. And if I measure with B, I get a number out. Okay, so if I know what my two operators are, I can calculate this commutator, the difference between flipping the order. And if I get a non-zero answer, then I can't have a wave function that is simultaneously defined for both properties.
Does that say if two operators
Commute.
Oh.
Commute. AB versus BA. Commute. I'll write that. Maybe the U is a little hard to read there. Commute. Right? Remember the commutative property in algebra. A times B is equal to B times A. Right, so you might think, okay, in algebra, we always assume that A times B is equal to B times A, right? The commutative property. I'm going to show you examples in this class, and just now, in the next 5 minutes, that don't commute. Operators cannot necessarily commute. And in fact, I really want to show you this with I can actually show you with a die. That's why I asked people at the beginning of class for a D20. I can actually show you, it's not a quantum mechanical property, but you can actually show that rotations, if you think about operators as a way to rotate objects, right? You rotate 90 degrees along this axis or this axis. If you commute rotations in a three-dimensional object, you'll find that you end up in a different spot than you did when you do it one way. So if I do a rotation along one axis this way and then along a different one, the other way around, and then flip it, I end up with a different final point, a different edge of my die. Rotations in 3 dimensions aren't commutative, right? So you can't just flip rotations and get the same thing out. It's really easy to see once you do it with a 3D object, but I'll bring one on Thursday. So it's not a quantum mechanical thing. There are things in real life operations that you can do that don't commute. And what does that mean? That means that in quantum mechanics, if you have two things that don't commute, two operations that you do on your system to do something to it, measure it or whatever, they don't commute, then the wave function can't be defined for both properties simultaneously. So let me give you some examples. So operators that do commute, there are lots of them, but I'll talk about a little bit of a few that we've already talked about. Right? One is the Hamiltonian and position. Right? We know that this works because we solved the Schrodinger equation for the harmonic oscillator. Right? We came up with a set of wave functions that satisfy the Schrodinger equation for the Hamiltonian. And we measure x for them. Right? We do it all the time. We've done it pretty much every single homework. Right? So we know that these commute because we can measure energy and position at the same time. Here's another one. L squared in H. Of course, these two commute, right? And we just saw why they commute. Because for the free rotor that we've been talking about, H is related to L squared by a constant factor. They're basically the same thing. So, of course, they commute. And not surprisingly, L squared and L sub z commute, right? I can prove that they commute because the wave functions are spherical harmonics that depend on both quantities, right? This is Lz, and this is L squared. Right? So these two commute. We can measure them both simultaneously. Right? So you've seen some of these kind of implicitly, that these are things that we can talk about at the same time for the same system. But there are classes of operators that don't commute. And I'm just going to derive one right at the end. Here, it's just going to take just a minute to prove to you that there are operators that don't commute. So what about, so I'm going to call this commuting fails. One of them is momentum and position. We've kind of talked about this before. You can't know momentum and position simultaneously. Once you know one, you lose the other. And we talked about this in homework 1 and in a particle in a box. And when you measure these like this and you do the commutator, they're different by IH bar. Let me prove this to you. Really, really easy math. Remember that the operator for x, you have to go back a long time ago, is x. And we very rarely talk about momentum. But momentum's operator is minus IH bar times the derivative with respect to position. So let's derive this expression. X comma p is going to be x hat times p hat minus p hat times x hat. What I'm going to do is I'm going to add a psi, a wave function, to the outside of this because it helps us a little bit see the math. So I'm going to FOIL this. I'm going to distribute this out. This is taking the measurement of the measurement of momentum first on the wave function, then measuring x, and then subtracting from it the momentum measurement after we measure the position. Okay. So let's do the left-hand side first. This is going to be x times minus IH bar times the derivative with respect to psi. That's the left-hand side. Or sorry, the left term. And the last term will be minus IH bar times the derivative of x evaluated on psi. Right? You may already see that these aren't going to cancel each other out. Because here I have x times the derivative of psi, and here I have the derivative of x times psi. Right? We have to use the product rule over here. So let me just simplify a few things. We get an IH bar out. And let me actually factor out, my IH bar. And we're left with x d psi dx. I factored out the IH bar, so we have a plus here. Oh, sorry, I have a negative sign here. Sorry, I apologize. There's a negative sign here. Let me erase this. negative x d psi dx plus the product rule, the product of the derivative of the product of x psi. So that's going to be d psi dx plus psi. Right, so we're taking the first term is d psi dx. That's where we take the derivative of, sorry, that's wrong. I apologize. So we're going to take the derivative of x first. That gives me psi. And then we add to that the derivative of x times the derivative of psi. D psi dx. There we go. Okay, if you might notice that the derivative terms cancel out. We have a negative one here from the first term, and we have a positive one from the second term, so these cancel out. And we're left with that xp, the commutator of xp evaluated on psi, is equal to IH bar psi. Right? And that gives us the answer, right? If I delete the psi, right, I get that the commutator x and p is IH bar. Now, what does that mean? That means that if I measure momentum and then position, and then subtract off the opposite where I position and momentum, my wave function is different by this complex factor. Remember what a complex number is. It has something to do with a rotation in the complex plane. Remember, these are complex waves. They're two-dimensional and they're imaginary. And this is h bar, right? This is angular momentum. So when I measure x and then measure p, or I measure p then x, the resultant wave function that I get out from either one of those two measurements are different by some phase factor, some rotation in the complex plane. They're now pointing in different directions. Right? So if, for instance, my psi initially is, let's think about color and flavor. My color is initially white, and then I measure flavor. The color's been mixed. Right? It goes back to white plus black. Exactly the same thing here. I measure the momentum of my system and then measure x, and then subtract off the opposite. And what I've done is the net difference between those two results is some phase factor in complex space. I've manipulated the wave function. Therefore, the wave function isn't constant. Therefore, I can't measure x and p simultaneously. Right? I can take this information and I get what's called the Heisenberg uncertainty principle. Right? We'll talk about that on Thursday. Just very briefly, we'll talk about that consequence. But this is the direct result of the Heisenberg uncertainty principle. This is where it comes from. It's the fact that when you measure x and p, it depends on the order you do it. It affects and manipulates the wave function, just like color and flavor do to spin. All right, so we'll see that next class. So we're at the point now where we can take these rules and start thinking about angular momentum. And we'll look at the commutators of angular momentum, and then we'll start to see that there's a good reason why we can't measure all the directions. Because we're going to find that the commutators don't work. They give us a non-zero result. And we'll be able to use that information to derive something about angular momentum, and that will allow us to actually go right into spin. Once we understand this and be able to work with commutators a little bit, we can actually understand the spin of the electron. And by the time we're there, we'll have a complete picture, as of Thursday, a complete picture of how the electron moves in an angular fashion. Okay? And it's all built into this idea that we can only measure one direction at a time. All right, you guys have a good week or a good day. I will see you all on Thursday.
Bye, Surfer.
Bye, take care.